All right, well, I just want to thank everybody for attending. This is Intech's engineering webinar for the first quarter. I'm going to cover tiebacks and soil screws 101. This is, let's see if I can get this slide to advance. All right, so this is going to be the webinar timeline, planning on going about 50 minutes and then take some questions, and there will be a quiz that'll be on a separate platform, but basically, I'm going to go through each of these points: introduction, safety, slopes and walls, tiebacks, the specifics of helicals and hollow bar, micropiles, post-tensioning load testing, and then I'm going to talk about soil nails and screws, and then I'll open it up for questions. All right, so brief introduction. I represent Intech. Tim Combs is our president. Bill Sears and Luke Curley are our sales managers. Sam and I are the engineering staff. Then we got Josh, Chris, James, and Eddie are our warehouse management and staff. And then Jim Sorrell is our Hydroway sales manager. We represent multiple brands. Chance and Atlas is our helical and resistance pier line. Their Hubble is the manufacturer. MagnaCore is our non-domestic hollow bar micropile line. It's a hollow bar, so it's a little bit different than the conventional solid bar. It's got some benefits I'll talk about later. Hydroway is our geosynthetic wrapped strip drain product. I'll talk about it later, but we can use that behind retaining walls and at the facing for drainage. And then we also have our carbon fiber reinforcing carbon bond. It's carbon fiber strips with resin used usually for crack repair and some structural reinforcing. If you go to intecanchoring.com, you can find a lot of good information and reference materials. I'm pretty happy with how our website's going, how it looks. So typical project flow generally starts with a consultant generates recommendations, the owner engages with the general contractor, the contractor engages a specialty contractor who then installs the elements and the project gets completed. We can add our value in multiple different facets in every part of the project. With consultants, we'll provide this education and resources so that you can use it for design, figuring out relative costs of things. And we also complete design submittals that we're not an engineering company, but we do lean on engineering companies for liability reasons. So there would be opportunities to complete design submittals. For the owner or the general contractor, the same thing, we provide this education and resources, but we also have a large network of installing partners who we help train, we help get them the knowledge to how to install these things correctly. So we can help with that. And then the specialty contractors, the people who are actually putting the elements in the ground, we can assist with design submittals. We complete the engineering portion of it and have the engineering liability signed off by a licensed engineer, construction phase assistance, specialty testing, and guidance. So we can add our value in all of these different ways. We have two locations, Caseyville, Illinois, and Livonia, Michigan. It's Detroit and St. Louis. We represent for Chance and Atlas, one of their distributors. We represent this greater Midwest service area. So for the helical and resistance pier lines, we can sell within these states and zones. For MagnaCore, our micropile line, we can service the entire United States. And then Hydroway, we're able to do it worldwide. We have some international partners that we deal with. So I like to start every presentation off with a talk on safety. Everybody has somebody that cares about your safety. If you do a thought experiment, you could imagine you're on a job site or you're explaining to somebody who you love or somebody you work with that cares about you, what you do. If they saw that, would they feel comfortable with what you're doing? And try and look at it from their lens. It's a pretty powerful tool, or if you saw somebody doing something that was unsafe, you should let them know that you feel that it's unsafe and they should figure out a different way of getting the job done. So go home safe every day, period. Specific to the elements that we install, these are some of the safety points that I like to talk about. Out on job sites, there's a lot of overhead equipment, moving construction equipment, swinging arms, excavators and whatnot. Utilities, you got to know your local requirements. Make sure you call your own utilities for yourself. Don't let somebody else call in your utilities for you. OSHA and shoring requirements, make sure that you're following those recommendations. Eye and ear safety, inhalation, pinching points and cuts, just general wear and tear. Some of these, elements, can be a little tough to install, and you got to get in there. Just make sure you're doing it safely, and it's fine, Muscle fatigue and hydration. A lot of these jobs are hot conditions or cold conditions. Make sure that you're staying hydrated. Make sure that you're not overheating, stuff like that. So I'm going to get into the first topic, which is slopes, walls, and stability. Soils generally tend to find their natural configuration based on their inherent strength and depositional history. So over a long period of time, after a lot of rain events, seismic events, loadings, unloadings, the soils will typically find an optimal slope at which they're going to fall. But humans, through construction, like to alter slopes, and sometimes they want something that's steeper than what their strength allows. So we have to utilize an engineering system to facilitate this slope change so that there's not a failure immediately or down the road. So just a cantilever wall for informational purposes. So you have your original slope and you want to change the grade to this retained grade. You're basically resisting this overturning and sliding. So there's a lot of internal forces that are going on within the wall and the slope. So you got to make sure that you're considering, and this is specific for cantilevers, it could be different for other types of walls. You got to consider what the movements and rotations you're trying to resist are. So another thing that we have to consider as engineers is the difference between the local and the global stability wedge. So the local stability wedge is the stability of the soils within the influence of the engineered system you're putting in to resist the, to keep the wall up. The global stability wedge is something that's outside of that system. It can go pretty close to that system, so it can be pretty close to this wedge for your global stability, or it can be very, very far out. So that has to be considered for every project, and it has to be done by a licensed geotechnical engineer. Global and local stability, like I talked about. So factor of safety needs to be considered, and your factor of safety is just the ratio of your resisting forces to your driving forces. If your resisting forces are far greater than your driving forces, your strength is greater than your force, you're going to have a stable system. You have to consider how stable you want that system to be, and there are guidances out there based on the project that recommend certain levels of factor of safety to use. So you need to know what you're designing to, whether it's 1.0, 1.3, 1.5. You have to use the correct applicable factor of safety for your methodology. So a brief talk through on tieback walls. This is a representation of a bunch of different walls, and I've highlighted the tieback wall. One thing to note about this is the tieback wall is typically a top-down wall. So for instance, I'm going to do this pile and lagging wall. You start by driving your piles into the ground, starting at your original grade on both sides, and then you have planned excavations, say 1 foot increments, for example. You go down to your first anchor element point and you excavate to that a little bit below that. You'll put in lagging if it's that type of wall in this step, and then you'll install your element. So typically 10 to 20 degrees is what we see, but it can vary from there for a tieback wall. Also, it's important to note that load testing and your termination should be performed from this point before you excavate the rest of the wall. So then your remaining soil is excavated and you can put your facing on the front and finish everything out. So an elevation and plan view of these, how these end up in the ground. So I'll start with the elevation view. You have your piles and whaler that comes across. Your bearing plate and nuts will terminate onto this whaler and transfer the load from your anchor into the whaler, into the soil, into the piles and soils. So plan view, you have, I included the lagging in there, but you just basically have your element going into the retained side of the soils, and you're just gripping behind the failure plane. Anchor failure mechanisms, depending on the design methodology you're planning on using, you have to consider the failure mechanisms. So this is out of FHWA Circular 4 for the Micropiles. This is what they recommend to check, and just make sure that you're checking what needs to be checked per the specific methodology you're using. One other consideration you want to have is that when you batter an element, there are components to that battered element that will vary depending on how you batter it. So what that means is if you have a shallow element, the vertical component won't be as large as the vertical component of a steeper element. And you have to consider this vertical component in your wall facing or in your wall piles, because those components of your element will add to the vertical load of your piles in your wall. So you have to make sure that you iterate it with your design to make sure that both of the whole system can work, that you're not just designing something that won't ever work. Basic design principles for helicals and micropiles. I'm going to start with helicals. So for helicals, the essential elements are you have a shaft, you have at least one bearing plate, and then you have a termination. For tiebacks specifically, this threaded adapter is going to be the termination, or some variation where you'll have a plate on the other side of the wall and you'll thread everything up against the wall. You're basically transferring the load from the wall to the termination to into the shaft, and then the bearing plates engage with the soil to give you your capacity. The geotechnical capacity of the element is the bearing capacity at the added up individual plates. So each of these flights or plates will have a pressure bulb that, as long as you're not exceeding the geotechnical bearing capacity of the soils in front of that, then you should be good. And you add up that ultimate load with each plate. One important feature of these anchors is that they are screwed into the ground. They're not drilled, very low displacement. You're basically moving the soil out of the way so that it can re-engage onto your element at a higher strength. Some of the pros of using a helical versus other methods is there's a fast installation. You don't have setup time for grout curing. You can also remove and reinstall an undamaged element. So if you screw these into the ground and you maybe don't get capacity, or you think that you can get it in a spot next to where you're at, or you refuse early and need to move it over because there's an obstruction, you can reverse your screw out and then relocate it and reinstall it. Another feature of these is that they're self-testing. And I'll point out where you would put this, but you have a torque monitor that goes in line with your drill string, and it'll measure the torque. As long as it's calibrated, it'll measure the torque so you know what you're at. One of the biggest problems we have is it can be somewhat problematic in dense cobbly or hard profiles. We do have some solutions for these issues. We have a rocket lead, which has a carbide cutting tip on it that you can get through some denser profiles, but if it gets really cobbly, it can become problematic to install these. So this is the wordy version of the installation. You put your lead section on, you put it up to your face, orient it at the required installation angle. You screw your lead section into the face, making sure that you're installing the angle, or making sure you're maintaining the install angle. You attach an extension, continue installing, repeat, and then once you get to your required torque, you proceed to load testing and termination. And so this is a picture of an inline. You put this in line in your drill string and it'll measure the torque for you. So that's the wordy version. Here's the visual version for people who are visual. So you start with your drill string and you put your lead, which is the one that has the plates on it. So you have bar and plates on it. You put that up to your excavation face and you put it at the angle that you want to install it at. Then while you're applying both crowd and torque, you screw the anchor into the soil face. So you're pushing down while you're turning, while this lead is turning, and it'll screw it into the face. Then you take your drill string off, your drill head off, you put an extension on to this bar, and then you put your drill back on, and then you screw that into the face. And you keep doing this, making sure you're affirming your installation angle at each time. And then you do that until you get to a torque that you want to get to for your design capacity. So once you get to that point, you're terminating these things, post-tensioning, load testing, whatever you want to do, then you terminate it. So this is the representation of the general design principle. Basically, you install this element behind your theoretical failure plane for your wall type. Once you're past that failure plane, a minimum of 5 times the largest helical diameter, you can count on these plates for the geotechnical bearing capacity. So for the deep foundations in clay, the N sub C turns into a 9. And for sands, then you're depending on your overburden and your N sub Q. So 2 considerations have to be taken into account. You have the geotechnical and structural capacity after the element is installed. So once you have everything in the ground, what is that capacity? But you also have to consider that while you're driving these things, there could be a variable soil profile that maybe it's denser in some spots than others. Are you able to get through this section of soil to get to your bearing material without over torquing your bar? That's an important thing. So you have to always consider those 2 things, and I'll talk about how we estimate that later on in an easier way. So basic design principle of helicals for estimating the capacity is there's an empirical relationship between the measured torque and the estimated pile capacity by a number that we call K sub T. And that's just a number that has been load tested throughout, thousands of load tests. For square shaft bars, the K sub T value is 10 foot to the minus 1. So if you wanted a 20 kip pile, you would have to do 20 kips equals what torque you want to get to times 10. So it would be 2,000 foot-pounds. For round shaft, however, it is variable depending on the size of your bar. So if you wanted to do that same relationship, and I'll say 18 kips, so you'd have to do 20,000 or 2,000 foot-pounds times your 9 for a 2875-203. That would give you your torque. So this is a way that we pretty quickly determine what torque you have to get to for installation, but it's always important that you verify with load tests because that's the only way you can verify the actual capacity of your pile. HeliCAP version 3 is a software that we use to determine the capacities of these elements pretty quickly, pretty efficiently. So I've included this link on there for the HeliCAP software. Additionally, there's now some how-to tutorial videos on the same link that go through setting up your project, setting up your soil profile, and completing an analysis for both Tiebacks, soil nail walls, and tension and compression vertical elements for underpinning. So if you guys want to use that, it's available. You have to sign up. Really quick run through of the software. You just start off with entering your job profile, what your project name is, whatever contact information you want to put in there. Then you select your application mode, which for this instance, I put Tieback. And then you fill out your soil profile. You fill out your profile above 0. So if you have any back slopes or anything like that, your anticipated failure surface. So that envelope that we talked about earlier that you have to get 5 diameters past. And then, so then you click on this series button and you enter your element information in this box. So 20 foot long, 10-degree installation angle, 3 foot down, square shaft, 1.5 inch material. So you enter all that, you insert your anchor, which will then put it in your soil profile, and then you hit calculate. Once you hit calculate, it'll give you your output of your recommended horizontal and vertical components that your element is going to give you. So for this one, it's 12.1 kips in tension. And you can see that that pretty much correlates with the 10-to-1 ratio of torque to capacity, having 1229 foot-pounds. So it's just a tool, though, to get estimates in quickly. So here's some square shaft and round shaft helical product capacities. If you want to know, if you know what your load you're looking for is, you can figure out what bar type you want to use. So I've been talking, the bar type names. So you have a product series that is called by the square dimension. So this SS 125 is 1.25 inches squared. And then for the round shaft, 2875 is your OD, and then the 0.203 is your wall thickness. So now I'll talk about hollow bar micropile anchor tiebacks. Basic components, you have your nuts and plate at the top. You have your bar, coupler, centralizers if they're required, and then your bit at the bottom. Basically, and I'll show you in a similar way that I did for the Helicals how these get installed, but basically you start with your lead. You start with your lead with a bar, you add a coupler, you drill it into the ground, and you'll have grout coming through this whole string the entire way down. There's little ports at the bottom of the bit, and there will be grout coming out of it the whole time. And you just keep drilling until you get to whatever length you need to get to based on the boring logs, and then you leave everything in the hole and you terminate it as is. So this whole element will end up in the ground. You don't have a separate steel that you replace your drill string with. We have different bit types for different types of soil profiles. Carbide button bits if you're into relatively deep rock sockets. Carbide cross bits if you're in a mixed profile. This will even work for some sandstones, shales, and fractured rocks. And then we also have a clay bit. So I talked about essential elements: hollow shafted bar, couplers, termination, and sacrificial bit. Bits have ports, like I talked about. Some of the pros is you can go through a pretty dense cobbly profile or into rock. There's a hammering function that the drills have that if you get hung up onto something dense, you can hammer through it. And we've had some demonstrations where we've easily gone through concrete within a couple seconds. A big 6x6 block of concrete, we cored a hole in it within 20-30 seconds. So it can get through some pretty good stuff. Another pro is, we don't design with this per se, but there's grout leaching into the soils, creating even better engagement in the soil. So what this means is there's this dark gray band of grout around the column, and it's about the same diameter as the bit. So that's what we design based on. But since we're drilling under pressure with the grout, it's going to leach out into the soils a little bit better than just being within this annulus. So there will be some increased engagement between the soil and the open grout, I'll call it. So you'll get typically a lot higher capacity than what we're designing with. So it gives you an even better factor of safety, a better peace of mind. So cons, you're using grout, so you have some temperature fluctuation problems to deal with. You got to make sure that you're not, setting up early or not setting up based on the temperature outside. You got to wait till it gets strength to be able to test it. And there's also, compared to the helicals, there's not a strength measurement during installation. I mean, you can get a feeling-based feedback and know, okay, I'm in, maybe a weathered shale versus the clay that I was in, or, oh, all of a sudden I'm in limestone. You'll be able to tell that, but there's not any sort of correlated strength measurements that you're getting in the same way. So installation method, you attach your lead section with a coupler to your drill, you put it up to the face, make sure that you go at the angle that you're supposed to do for design, spin your lead section into the excavation face, maintaining your install angle and hammering if necessary. While you're advancing, you're pumping grout through the entire string and it creates a jetted annulus approximately the diameter of the bit. You attach a coupler to your next extension section and continue installing. And then you repeat this until you're at the length that you need to get to, including rock sockets if required. Then you would proceed to load testing and termination. So similar as before, you have your drill, you put it at the angle that it needs to go to, you up at the excavation face, you drill while having this annulus being full of grout the entire time. You take your drill head off, you add an extension. These ones are typically 5 to 10 feet extensions. Make sure that you're at the installation angle that you need to be at, because this is going to be wet grout, so you have to make sure that you're checking that every time for sure. Then you keep drilling, and then you repeat that until your desired length / rock socket is achieved. At that point, you're going to do post-tensioning and termination as required. Like I've said before, hollow bar, your bar, your couplers, your bits all stay in the hole. They never get pulled out unless you have a problem and have to work on it. But we don't really run into that too much. Here's some strength characteristic pieces, so you can use that for when you want to know, okay, I have this strength element that I'm designing for, what bar type do I need to use? These designations right here, R32 would be the thread type is the R or the T, and that's rope or trapezoidal threads. And then the 32 millimeters is the diameter of your bar, and there's also a wall thickness associated with it, but that's a different topic. So some of the benefits for having a hollow bar is you don't have to worry about pre-drilling. You're drilling and creating your element all at the same time. You can go through really dense materials because you're hammering through the element itself. The energy is transferred down through the drill string to the bit. You can hit rock at any depth and go through it. It can be installed in a lot of soil types because you're not as worried about holes collapsing or stuff of that nature. You can case it for lateral loads, grout and bar installed simultaneously, and you only need a rock drill and grout plant because it all works as its own system. So basic design principle for the micropiles is you have this active loading zone and deepest points of your potential failure mechanism. You want to get beyond that point and only count on the friction along the element at that point. So for this zone before your deepest point of failure wedge is your unbonded length, and everything after that is your bonded length. Basically, you have your friction times your surface area of the outside of your cylinder of your micropile, and if you divide that by a factor of safety, that'll give you your allowable load. Post-tensioning, want to put a disclaimer, never allow anybody to stand behind an element while it's being tested. If anything comes loose, serious injury can occur. So post-tensioning, you can do this on either helicals or micropiles in the tieback application. You're basically pulling on the element so it results in an active support condition. You're actively pulling the wall towards the soil, towards the element. You're having a reduced strain compared to a soil nail wall. By post-tensioning, you're taking out that, since you're doing an active condition, you're taking out that not slough, but potential strain that could happen. It's less conservative than a passive anchor. You can have a higher peace of mind because you're doing load testing on each element and torque readings. You're getting torque readings if you're using the helical tieback. So a visual of what post-tensioning is you pull on the anchor to elongate it. Then while it's still elongated, you put a nut onto the anchor, locking it off. So you'll maintain this elongation after the nut is locked off. So this is done by a series of components that I have here. Basically, you first thread this nut onto the bar, but you don't finish threading it. Then you put what we call a load chair over the top of the bar that will seat against your whaler plate. And it's got a hole here that threads over the bar. So you've got this gap that you've created that you can, once it's post-tensioned, you can thread this nut the rest of the way. Then you put this hollow ram jack over the top of the bar onto the load chair. Then you put a plate on, put a nut on, and then that's the setup. So basically, when you engage this jack or this ram, it's going to push against this plate, which is going to push against this nut, which is going to strain this bar, and it's all reacting against the load chair onto the whaler bar, whatever you need to do. So while it's elongated, you're going to thread this the rest of the way, and it's going to be locked off. For post-tensioning, making sure to measure all of the deflections and whatnot, this would be the setup. You have your load test setup or your post-tension setup over here, and then you have a leveled tripod that has an arm that reaches out, or with a dial gauge on the end that's touching a plate that's going to linearly travel with the elongation, the axis of the bar. Seen other things where you have, just a 2x4. I wouldn't recommend that. Maybe some steel channel or something like that. Something that's going to hold its rigidity throughout the process, because you don't want that to move because it could create errors. So for tieback wall lock-off load, you're basically post-tensioning it, you're load testing it, and then you have to leave it at a certain design load before you lock it off. So this is the design earth pressure envelope. This is what we're using to estimate the anchor load that you need. Typically that overestimates what's actually going on behind the wall. So this is the actual earth pressure. So you wouldn't want to over tension your bar, because you can create failures in your wall. You can create failures in your facing. Typically what I see is a recommendation of either 70 to 80, somewhere in there. FHWA has some caveats for where they would say to go up to 1. But you don't want to go over 1 times your design load, because this overestimates what's actually going on behind your wall. Obviously, use engineering judgment. This doesn't apply for everything. Make sure that you're utilizing the proper design methodology per your project requirements. And make sure you're using the right earth pressure envelope as well. Load testing, same thing as the post-tensioning. Don't ever allow anybody to stand behind an element being tested or strained. You can get hurt pretty badly. Simplified load test steps. Use a specific design methodology, load test recommendations. These are just generalization. So you install your element, you apply an alignment load, your seating load, which is typically 5% your design load. You load your element to the first load step and you hold, recording your deflection. And then depending on the type of load test you're doing, you either advance to your next load step or you bring it back to 0. So you repeat that process, going to your next step, and then reducing to 0 or advancing. until you get to your maximum factor safety times your design load. Once you're there, you hold it for a creep test if that's required, and then you reverse per the load test schedule, recording deflections on the way back until fully unloaded. And then you plot and compare results with project thresholds. So these are two types of load tests. The cyclic load test is the one where you go to your first load step and then back it off to 0. And then you go to your next one and repeat until you're to your maximum percent of design load. So what that'll help you get is your individual residual movement per load step. So I know that load step 50 caused, this much minus this much worth of residual deflection in the soils. And that'll help you, reduce or modify your design so it's more efficient. You know what each individual load step is actually doing to the soil, versus over here you have the incremental load test where you're advancing to the first load step, recording your deflection, and then you advance to the next one and so on. So in this one, you really only know what your overall residual deflection would be. So for micropiles, FHWA circular number 4 goes through this. There's 3 types of load tests that they recommend. The first one is a performance test. This is performed typically on a first couple production elements. You're doing a cyclic loading, unloading. You can verify your capacity, your load deformation behavior, identify different causes of movement, and verify that the unbonded length is greater than design. So that just means that you are counting on less than what you designed for in bonded length than what you designed for that load. So you're getting load with less bonded length than you originally designed for. Proof test, it's an incremental load cycle, so you're advancing to the next load step instead of reducing to 0. So this is used as a less involved check. You're not going all the way back to the beginning after every load step, so it's a bit quicker. And if the results are vastly different on a specific element, so if you're testing 100 of them and number 78 all of a sudden is a lot different than number 77, you might want to do another performance test and see if there's something problematic going on at that specific location. And then there's the extended creep test. So if your creep test fails within 10 minutes, there's guidance on how long to retest it, but this extended creep test is an extended creep test, and you either devalue the load capacity of your pile or maybe reinstall a new one or figure that out. So for helical tiebacks, I would recommend using the Chance design manual that can be provided if you need it. Pre-production tests are typically optional. You're trying to determine the actual failure point of the testing so you can optimize the design and verify torque to capacity ratio of elements. So that K sub T value that I talked about earlier, that was an empirical number, so you can figure out what the specific torque to capacity ratio is at your site and get a more efficient design than what would be recommended by Chance. Performance tests are performed on a couple of production elements per project. You're doing your cyclic loading, so you're going up and backing it off to 0, up to 1.25 your design load, and then you hold it for 10 minutes for your creep test. This is like a full load test where you're trying to figure out all of the sources of strain and the strain at different spots of your loading. And then you have your proof load testing, which is your incremental load testing, 2 minutes held at each step, and then 5 minutes at max. This is performed on your remaining production elements, and you're just trying to determine if the consistency of the elements of the job is acceptable. Here's a quick chart or graph of a load test. Basically, you're considering this is the elastic tension in your bar, this is the elastic tension of your plates, and then this blue line is the measured strain. So this deflection at your load, this deflection is a result of your elastic tension in your bar. This green stretch is your deflection of your plate, and then everything from that point up to your line is the deflection of your soils. For micropiles, this is an example of an incremental load test. You have your individual load steps. The result of that, so you have 6 load steps. The overall residual movement, the movement of your soils is going to be this amount. Or if you're getting into the inelastic properties of the bar, that could also hurt that, but shouldn't be going that far, and you should know that ahead of time. So then this elastic movement will be recovered by the end of the load testing. So what are we doing when we're doing load testing? What is your acceptance criteria? Basically, at the start of a project, you have input information and you're creating a model. You're creating a design using calculations, using empirical evidence that tells you, okay, this is going to work. Then you go through and perform an installation of your element, and you get maybe some feedback based on the type of element that you use. And then you need to test the element to determine if what you put into the ground is acceptable, if it validates your model. So you got to validate that based on the capacity, the creep, the model characteristics, design methodology requirements, your minimum unbonded length. So then you have the possible outcomes. You either have an acceptable element, it shows that this specific element will give you what you need in capacity. You can remove and reinstall the element, which is especially easy if you have helicals. Or you could also derate the capacity of the element and install extra. So, been talking about tiebacks for the majority of the presentation, and I just want to start off by saying that there's a substantial difference between tiebacks and soil nails, soil screw walls. So the Chance Manual and FHWA go through and detail specifically what each of these are, and you can use HeliCAP and you can use snails to design these elements, but the elements are basically a passive element versus an active element. And what that means is with the active element, the tieback wall, you're putting tension into that element, so it's actively pulling back on the wall. These elements are reinforced soil earth walls. It's more like a mechanically stabilized earth wall in the fact that you're just creating a stable block. So also, I'm going to say soil nails and soil screws. This is the difference between a soil nail and a soil screw. A soil nail and a soil screw are very similar, except that a soil nail is a micropile and a soil screw is a flighted helical. Basically, it's akin to a reinforced soil wall, and you're literally just taking this block of soil and making it stable such that it resists any movement of the soils behind it. So it's fighting against the lateral earth pressures and the overturning and sliding of this soil behind it. So soil nails and screws are an internally reinforced soil mass system because you're putting closely spaced anchors protected by a reinforced shotcrete wall. They're passive elements, so there's no tension put into them, and it requires that the slope moves before it works. So if you never have any movement, you know that you did a good job. So it's more of an insurance policy. Typically, these are a shallower angle of installation because you're not trying to get to a bearing stratum that you can count on for bearing. You're just consolidating this material together so that it's stable. Similar installation method. You start with excavation of your initial lift. This is probably a little steeper than I would like. You drill your nail hole. You do some temporary facing, strip drains, have your tendon in there and your grout for the magnecore. This would all stay in the hole. You do your initial facing. which includes shotcrete, bearing plate, washer, reinforcement, hex nuts. And then you repeat that process vertically until you get to your final grade. And then you'd want to put your foot drain in, final facing, make sure that you have drainage control up top, because water is one of the most impactful portions of slope stability, local and global. So that was soil nails. Soil screws are almost identical. You excavate your bench, install your upper tier of soil screws, install your drainage strips, reinforcing steel and anchor plates, and put your initial facing on. And then you repeat that until you have all of the rows of your system. Here's a cross section of a typical soil nail wall. You can use this to reference if you're designing these, but you have your tendon coming through with your grouted section. You have your wall initial facing. You have a plate. You have a beveled washer, a nut, and then you have final facing over here. So screws, this is a typical cross section. It's very similar. Instead of having a threaded bar, like the Micropiles come through their threaded bar already, you have to convert this square shaft or this round shaft material into a threaded bar. So we have an adapter that you use to transition from square shaft to threaded bar to make that connection work. There's a soil nail patterns on your wall face. There's some typical values out there, but you just have to satisfy the design methodology in terms of how much the facing can take and how much load you can have in each element. The real purpose of this presentation, isn't so that you can design it right off the bat. I think that this should be a good topical overview of all the elements so that you know what you're looking at when you get into the design methodology. So soil nail length can typically be estimated to be efficient at about 70% of your wall height. If it gets too much longer than this, if it's required to be too much longer than this, it becomes a little inefficient. Some conditions where the elements might need to be longer, weaker soils, deep seated critical slip surfaces, large surcharge loads behind your wall, rising back slopes. Battered walls can reduce the required lengths, and make sure that you're considering both your geotechnical and structural limits during installation as well as post-install. Preliminary feasibility assessment. Whenever you're installing these walls, typically what happens is you do that initial bench, and you're doing it along a line that could be 50, 100 feet or more, and you're going to install your elements as fast as you can, but those soils of that bench are going to have to set up for a day or maybe even two. So it's important that the soils can be unsupported in vertical or near vertical cut 4 to 6 feet high for a couple days, 1 to 2 days. Naturally cemented or sands and gravels, those are good. Residual soils and weathered rock that don't have joints that are oriented parallel with your slope so that they would slough off. You don't want that to occur. Sands with some apparent cohesion, stiff cohesive soils that aren't susceptible to creep, and soils above the groundwater table. So like I said, excavation happens along a line and not all elements are installed immediately. So that was the end of the presentation. I was 1 minute longer than I wanted to be, so I guess that's good. If you guys have any other questions outside that you want to ask outside of the presentation, feel free to contact me. Where did my screen go? So now I will open it up to people to ask questions. I'm going to be sending an email out via this webinar at intechankering.com with the link to a quiz. once you guys complete that quiz, it's going to register a list for me to, generate and send out the PDH credits. So I think that I'll have that out within the hour. And then if you guys don't receive it, send me an email because I want to make sure that it doesn't drop off in people's junk boxes.